Gaussian elimination. So we started it last time with an example. And my example was minus 3x1 plus 2x2. I'm just going to rewrite minus 1. 6x1 minus 6x2 plus 7x3 is equal to minus 7. 3x1 minus 4x2 plus 4x3 is equal to minus 6. So I started explaining how Gaussian elimination, which is basically a procedure that will give me the solution. You probably introduced Gaussian elimination in your differential equations when you were reviewing linear algebra. Solving systems of linear equations is basically the fundamental numerical problem that any engineering branch has to solve, because a whole lot of practical problems, no matter what their origins are, come down to solving a linear system. And those that don't, they're solving nonlinear systems, which ultimately the way we solve nonlinear systems is basically often by linearizing them. Okay, so we're back down to linear systems. So linear systems are everywhere. That said, you might not even notice. Okay? Typically, it's built into the software you use, and without you even knowing, you might be actually solving hundreds of linear systems underneath, and then all you do is look at the ultimate solution. So this is why it's important for us to at least know the basics. Now, you have done Gaussian elimination in your linear algebra before. I will possibly introduce a slightly different variant of it. There's no like, oh, strict, super strict algorithms. There are small variations. My point is that here I'm going to introduce an algorithm that we can easily translate to code. Okay? And the whole point of introducing algorithms is that we can actually then see how to program it ourselves, so you know how to use it. So first step in one of these algorithms that go under Gaussian elimination umbrella is to take this system. I'm gonna, and that's what we did last time, create an augmented matrix out of it. An augmented matrix is simply a matrix of coefficients from left-hand side. Okay? So in this case, I have a 3 by 3 matrix. Okay? And then I just do a line, and I'll put the right-hand side on the right-hand side of that line, minus 1, minus 7, and minus 6. So we call this augmented matrix, and it really has form of A, B, where I'm actually solving AX is equal to B. The reason to do that is simply I don't want to repeatedly write down x1, x2, x3 constantly, but I want to work with coefficients and change them. So first we are learning how to do it by hand, and then we will translate it to code. So what we did last time, we focused on transformations to this system that will essentially get rid of coefficients, or basically make them 0, that are below the diagonal. Okay? And then as a result, I have an upper triangular system that has zeros below. Did my solution to the system AX equal to B change in that process? No, that's why we can actually do it. So basically solving that upper triangular system is the same as solving the original. Why? What do we do to get to the upper triangular system?
So linear combination of the older.
Right, so basically if I have a solution to a linear equation, okay, so let's say that I have x1, x2, x3, such that minus 3x1 plus 2x2 plus minus x3 is equal to minus 1. I can multiply that whole thing by 2. I didn't change anything. I didn't change x1, x2, x3 themselves. Just by multiplying my entire equation by 2, or whatever other number other than 0. Right? But if we would multiply things by 0, then we wouldn't get far, right? Second thing is the same thing if I have x1, x2, x3, that is solving the first equation and second equation. The same x1, x2, x3 is solving 2 times first equation minus 3 times second equation, or whatever other linear combination of those equations I can pick, right? And you can just see that algebraically. So we can do transformations of this kind as much as we want. We will not change the solution to the system. However, we will do them so it's actually easier for us to actually find that solution. Okay? So first step in that is basically to come up with, so for instance, I could replace this row by 2 times first row plus the second. So 2 times minus 3 is minus 6, plus 6 will give me a 0. Okay? And we did a number of those. So I'm not going to repeat all of it, but basically we arrived at the following thing. So where we ended up last time is something like this: minus 3, 2, minus 1, minus 1, 0, minus 2, 5, minus 9, and 0, 0, minus 2, 2. And I can already tell you, this type of problem on an exam is usually straightforward, except for calculation errors. So basically, you still need to practice, even if you understand how to do it. Practice will give you also the accuracy. So you need to solve a number of those problems to actually get things right. Okay, so now I actually have this form where these are zeros, right, that I'd like. So this system right now is what I call upper triangular. And it is ready for back substitution. And back substitution is essentially what you would do with this system. Which equation is the easiest to solve? Last one. So that's where I start. So basically my first step is minus 2, and I'm going to refer to that still as equation 3. Minus 2x3 is 2, so x3 is equal to minus 1. Then I can plug that into equation number 2. So I have minus 2x2 plus 5 times minus 1 is equal to minus 9. So my minus 2x2 is equal to minus 9 plus 5 minus 4. That gives me x2 as 2. And finally, the first one, I plug in everything that I know. So minus 3 x1 plus 2 times 2 minus 1 times minus 1 is equal to minus 1. So minus 3x1 is equal to, this is a 5 minus 6. x1 is equal to 2. Okay? Great. So I have x1, x2, x3. Can you check for me that this is the solution to the original system? Mm-hmm. Plug it in. I suggest plug it into one of the equations. So which one are you plugging in? First one? So minus 3 times 2 minus 6 plus 4 is minus 2. Minus minus 1 is -1. Works out. Can you check equation number 3 for me? Whether this solution is... It is? All right. So basically, for instance, number 3, quick check 3 times 2 minus 4 times 2 plus 4 times -1. I'm going to trust you that it's -6. Okay? So basically, if you do that quick check and just pick one of the equations, okay, the third one you kind of change the most because that one we replaced the most. Check on the third one that it works, and that's your quick check during the test that you actually got, that you didn't have any problems in calculations. Again, small calculation errors creep in easily. And that's about,
Are we going to need to do like 4x4s and 5x5s, or just
by hand? No, that's what computers are for. So that's
There always be a unique solution, or will there be two variables?
Thank you for that question. We're gonna jump to the equation that shows us. So no, as we said, there's no guarantee just by looking at the system that there is a unique solution. Okay? So I'm gonna skip to that example, and then I'm gonna go back to partial pivoting. Since the audience asked that we actually have if I can find that example. Wait. No, maybe I do need to go in order. I'll do partial pivoting. Oh no, I found it. All right. So that is essentially one way to solve. So basically now I'm gonna go to okay. And save this. Save. Control open. My sketchbook is not control open. Yes, save. Alright. Okay, so here's now an example, and so question was, is there always going to be a unique solution? And just by having a 3x3 system that I start solving, there's no guarantee that there is going to be a unique solution. But I'm going to actually introduce a very small 2x2 problem where we're going to discuss all of the possibilities. Okay? So let's do that. Example says, okay, find all solution, find, not fill, solution possibilities based on values C, D for this system. 2x1 plus x2 is equal to C. 4x1 plus dx2 is equal to 7. It's a small system, but still we can discuss what possibilities do we have based on C and D. So we're going to proceed as follows, as usual. So I'm going to create myself an augmented system and start working with my Gaussian elimination. So basically my corresponding system is 2, 1, C, and 4, D, 7. So in Gaussian elimination, I'm going to start getting rid of coefficients. This is my augmented matrix. Coefficients below diagonal. What coefficient is that? Who am I trying to make 0? The 4, yeah. So, and that's the only one actually. Yay, 2x2 systems. So how am I going to do it? What do you suggest? We replace this second, this is my second equation. What should I replace my second equation with? Negative 2 times 1 plus 2. That works. What else works? 2 times 1 minus 2. Okay. What else works? 1 minus 1 half 2. That works too. Just a little more calculating. Okay. What else works? Well, I can keep going, right? So a lot of versions work. When coding, you will have to be really clear about which, stick to only one option, but also in those cases, computer will do calculating for you. And when you're doing things by hand, you're welcome to eyeball and figure out what's simplest for you to calculate. Okay? All right, so let's stick with this first one. So again, many options could work. So let's just stick with this one. First, I have 2, 1, C. And then, so if I have minus 2 times 2 plus 4, that's precisely 0. That's by design. Okay. Minus 2 times 1 plus D is, D minus 2. Minus 2 times C plus 7 is 7 minus 2C. Now I have to imagine what are the different options that I could have based on D minus 2. The way I would go and solve this, okay, if this was now just numbers, is I say, okay, this times x2 is equal to this, so my x2 is simply this side divided by D minus 2, correct? Yes? Well, that has to be possible. And it's going to be possible if D minus 2 is different from, I'm dividing by it. So what's not allowed? Dividing by 0. So first case you discuss is, well, what if it's not 0, then we can do it. Okay? So our first option is D is different from 0, and therefore D minus 2 is different. D is different from 2, so D minus 2 is different from 0. We can divide by it. Okay. So in that case, I will have that D minus 2 times x2 is equal to 7 minus 2c. So my x2 is simply 7 minus 2c over D minus 2. There's something that crept in here. So if I have a 0, 0 here, this is allowed to be 0. But if this is 0, then I actually don't have this equation. 0, 0, 0, that's not an equation. So I have to discuss that separately. So for now, I will also assume and 7 minus 2c is different from 0. So my c is different from 7 over 2. So those are my special cases. Why? Because otherwise I would have 0, 0, 0. I'm going to write that here in blue as a comment. Otherwise, second equation is 0 equals to 0. Math has no problem with it, it's just not useful, okay? Okay, but not useful in limiting my choices. So if I have these two things, so D and these as true, then x2 is this, and my x1, well, I simply find out what my x1 is. 2x1 plus x2 is equal to c, so my x1 is 1/2 c minus. I'm just gonna leave it at that. Figure out the algebra here and figure out what x1 is. So in case that this is different from 0 and this is different from 0, I have a unique combination x1, x2 that solves this. So this is unique solution x1, x2, and this is my x1, this is my x2. Yes? Now let's discuss the weird cases. Let's go to this case. Did everybody write down? So let's go to this case. I'm going to call it case 2, where d minus 2 is equal to 0. Or, yeah, d minus 2 is equal to 0. And 7 minus 2c is equal to 0. So I have a 0, 0, 0. Did I discuss my d minus 2 was not equal to 0? Oh, we'll get to all of the cases. Okay, flip things a little. D minus 2 is equal to 0 and 7 minus 2. Then I have this second equation is 0 equals to 0. So it doesn't limit my system. And my first equation is as 2x1 plus x2 is equal to c, and my c is 7/2 from this, right? This is my solution. Okay? I don't have a unique solution. I have an entire line or infinitely many solutions, and the problem is that my second equation simply doesn't bring any additional constraints because it's actually a multiple of the first one. Okay? What multiple? This is my second equation from the transformed system. In transformed system, in original, my second equation is 4x1 plus 2x2 is equal to 7. Well, that's simply this multiplied by 2, right? And that's why it doesn't really constrain my system, because as an equation is the same thing. Yes. Same thing in the sense that the same x1 and x2 that satisfy the first one, that satisfy the second one, and the other way around. Questions? Okay. So I have infinitely many solutions. If I know how to write infinitely. x1, x2, and they're all on this line. 2x1 plus x2 is equal to 7/2. So I have one equation, two unknowns. And that's what we call underdetermined system. And the way you will typically report this, you will just simply express, so all of your solutions are in the form, like let's say x1, and then you just express what is x2 in terms of x1, 7/2 minus 2x1, so that's your x2, right? And then whatever x1 you plug in, that's what works as a solution to the system. So this sort of a parameterized form. And of course, if I had multiple equations, I could now have variations of this. If I had 3 by 3 systems and only 2 of those equations work, then I'm going to have 2 parameters, not just 1. Okay. And then my third case that I need to discuss is when d minus 2 is not equal to 0, but 7 minus 2c is still equal to 0. The weird case I'm going to look at in that case is that I'm going to have d minus 2 x2 is equal to 0. That just gives me, no, which one? This one is equal to 0, but the other one is not. Well, I should just looked at it because I flipped it in my mind. If d minus 2 is equal to 0 and is not equal to 0, I can still divide by it, and 7 minus 2 is equal to 0, my solution x2 will be 0. That's fine. That's a fine solution. x2 can be 0. There's no undetermined anybody. x2 is very determined that it's equal to 0. Okay. The problem here is, like here, I cannot divide by it, so I have to look at it, the equations separately and discuss separately. If I can correctly divide, I can just go with my old analysis.
What was the first one? The last one was
Underdetermined?
and
Yeah. The first one, what was the first one was just a unique solution. So it's just a regular system when I have 2 equations and 2 unknowns and all equations are independent, then I have a unique solution. So when I have this, then I'm going to have d minus 2, which is 0, times x2 is equal to 7 minus 2c. So the situation I have is that this is 0 and this is not equal to 0. This was my last equation, right? Is this possible? No. So just because I was able to write things down at the very beginning, that doesn't mean that all C and D numbers that I could possibly come up with work. So I still have to analyze the problem. So now it's possible, so there is no solution. Okay? And this is the case with parallel lines, right? There's no solution. So e.g. parallel lines. So indeed, if you go to the previous system, or my original system was, where's the write down of my original, which I keep losing in these papers. The first equation was 2, 1, and C. And the second equation was 4, 2, and 4D. So let me actually just write it. Let's just write it down what it is for this case. So it's save. So indeed, I had 2x1 plus x2 is equal to c, and then 4x2. If d minus 2 is equal to 0, d is 2, okay, is equal to 7, right? So when I multiplied this by 2, you would get 4x1 plus x2 is equal to 2c. So if 2c is different from 7, then I will have 2 parallel lines, essentially. So I will have same slope, but different starting point, and these two parallel lines don't intersect, so there is no solution. So graphically, if 2c different from 7, then these are two parallel lines that don't intersect, so I don't have solution. That's basically the exercise we had on the worksheet on Friday, right? Did you get those worksheets back?
Not yet, I'm 2,000.
There we go. Yes? Again, just because you can write the system down, that doesn't mean that it has a solution or a unique solution. So, conclusion, just because we can write down a system of equations, that does not mean it has a solution or a unique solution. And that is important because, quite frankly, as an engineer, most of your concern will be putting together physical laws and coming up with systems of equations and then letting the software, such as not that good for to find a solution. But you do want to make certain that whatever you come up with has a solution. Okay? Most often, if it doesn't, you introduce something non-physical. Sometimes you have to define or measure parameters, maybe you didn't do it correctly. So your physical measurements don't make sense, and therefore they're not going to make a solution. System of equations that make sense. Second problem, you might actually simply have a situation where you don't have a unique solution, which is okay. We're going to see actually cases like that. The simple case that I proved as that is that basically traffic flow problems, especially when you have lights that stop in cars and let certain flux, basically the way you optimize them is that you want certain flux of cars at certain speed going through. Of course you want a system that doesn't have a unique solution. I mean, if you only have the possibility to let through 5 cars at this intersection and 6 on this one and no more in 20 seconds, well, that's bad, okay? Because you're never going to get that unique solution. So you want actually something that, in order for traffic to work, it should be non-unique. But there should be a solution. All right. So what we played with so far is, okay, I pose a system of solution. The way we actually put together a solution procedure is that we manipulate equations. We can multiply one equation, add it to another. We can do that forever. Of course, we want to do that in a systematic way, so it gives us this upper triangular system then that I can actually start plugging in. I start at the end and start plugging in and solving. So that gives me a way to basically build down what my x1, x2, x3, and so forth are. Again, by hand, we're going to do 3x3 systems. For anything after that, I trust you can employ a computer to do it. And so I just want you to know conceptually what you're doing, so you can implement it on a computer. Now, before we get to the computer implementation, I want to point out one more thing, and that is one more thing that I can do with systems in order to actually make them more solvable or not change solution at all, is change the order of the equation. So which one I call first, which one I call second, which one I call third, doesn't really matter. But it does matter to a computer when you're trying to divide by 0. So we might want to avoid that. So let's see an example like that, and I'm just literally going to write down the example and we will actually solve it next time, but at least I have it written down. So in case we have a first equation, if I can find it in my notes, I can. Example that goes like this. 2x2 plus 3x3 is equal to 6. 4x1 plus 6x2 plus 7x3 is equal to minus 6. And 2x1 plus minus 3x2 plus 6x3 is equal to 2. That's going to be the system that I'm going to tackle next time. The main problem here is that I have a leading 0 here, and I need zeros here, here, and here. This coefficient 0 here does not help me in eliminating 4 and 2. So what I will simply have to do is flip the order of these equations before I go solve them, and that's called pivoting, or partial pivoting. So that's what we're going to do next time. So partial pivoting.
Yeah.